Knowing that at an instant shown bar AB has an angular velocity of 10 radians per second clockwise, and it is slowing down at a rate of 2 radians per second squared, determine the angular accelerations of bar BD and bar DE. Looking at this animation, we can see the direction of the velocity of point B and D indicated by the green arrows. Notice that also bar BD has some complicated motion. It is both translating and rotating. Some theory. Here is a bar that is both translating and rotating on the plane. It looks complicated. Well, it's not. It's just rotating around the green dot. This makes it look more obvious. That means we can apply the equations for simple rotational motion to figure out the bar's angular velocity and the velocity of each point on the bar. The bar's angular velocity is the same as the angular velocity about the center. However, in general, most examples of planar motion are not rotations around a center. Take the weird motion of this bar. However, for any small change in time, we can approximate its motion as a rotation around a point. By that logic, any planar motion at an instant in time is a rotation about an instantaneous center of rotation, like C1, C2, or C3. If you have a bar at a certain instant with known velocities at 2 points, you can find the center. During rotation, each velocity is perpendicular to a line intersecting the center. If you draw lines that are perpendicular to the velocities, they will intersect at the center. Here's the previous diagram and our knowns, the angular velocity as well as the acceleration of AB. This is our sign convention. Up, right, and counterclockwise are positive. Using what we just learned, we draw 2 perpendiculars to the green arrows to find C, the instantaneous center. Here are equations that relate speed and angular speed for simple rotation. The angular speed of AB is 10 radians per second. From this, we can get the speed of B by multiplying the length of AB by the angular speed. We get 2 meters per second. Now, the angular speed of BD, which is in pure rotation around C, can be found by dividing the speed of B by the length of BC, which is given to us in the problem as 0.25 meters. And now we end up with 8 radians per second. Remember, we want velocities, not speeds. So looking at the green arrows, we see that VB is to the left, so multiply by negative I, and omega BD, which is counterclockwise, so multiply by positive K. Now we can add these to our knowns. Just like before, we can find the speed of D by multiplying length CD by the angular velocity of BD, and we end up with 4.8 meters per second. We can now find the angular speed of DE by dividing the speed of D by the length of DE, which is given to us as 0.2 meters. And we end up with 24 radians per second. Again, we must indicate directions. Looking at the green arrows, VD is down, so negative J, and omega DE is counterclockwise, so positive K. Now we can add these to our knowns. We can use this formula to find acceleration from our knowns. Note that the formula only applies to pure rotation. AB is simply rotating around A, so we can use it. Using our knowns, we can find these 2 cross products and sum them. The acceleration of B is 0.4 meters per second squared, I, plus 20 meters per second squared in the J. Add that to our knowns. Simplifying our diagram, we don't really care about AB anymore. We now set out to find expressions for the acceleration of point D. We'll need this formula. However, this formula only works for pure rotations. In B's reference frame, or B fixed, BD is simply rotating about B. So we can apply the formula at bar BD to get this expression. This is the acceleration of D with respect to B. We know acceleration of D equals acceleration of D with respect to B plus acceleration of B. We can also apply the formula at bar DE, which purely rotates around E, for another expression for the acceleration of D. After this, it's just math. Again, we plug our knowns into these expressions, and the cross products are taken and summed. These 2 equations for acceleration are equal, so their x components and y components must be equal. Equating these two sets of components gives two equations with two unknowns. In the first equation, we can isolate the angular acceleration of BD, which comes out to be 305.6 radians per second squared, and it's positive, so it's counterclockwise. Substituting the angular acceleration of BD into the second equation, the angular acceleration of BD is 736.8 radians per second squared, and it's positive, so it's counterclockwise. Now let's take a look at our 3-bar linkage system in a simulated environment. Here's what the workspace looks like inside Simulink, SimMechanics, and MATLAB. The center portion here is our rigid system. We have a few prismatic and revolute joints, our world origin frame. We have our lower mount, our lower short link, our revolute and pin joints which connect the two, our equation solver for the system inside the simulation, as well as our middle long link, our upper short link, our upper mount, and now let's take a look at the sensor system that tracks the translation of each component. With the sensor system, you have the rigid transform sensor, which takes the inputs of translation off of each rigid body. We have the conversion sensor, which converts it from a simulated environment to data. And we have the XY graph plotting mechanism, or scope, that plots the data, as well as the two branches of the sim out, which take the data as input and send it over to MATLAB so we could use that data in a script or a run file. That pretty much sums up the workspace. Now let's go over to the simulation. Here's a copy of our simulation in the 3D environment. The black and white dots at the center of all the rigid bodies represents the center of mass, and you can see the respective origins and coordinate planes for each. If we run the simulation, you could see it go through its motions, and the 3 plotting graphs on the left-hand side. The top one tracks the instantaneous center, the middle, the upper link translation in meters, and the bottom one is the lower link translation in meters. The entire system is currently not under gravitational forces, but is rather actuated via an actuation motor that I've integrated into the top mount revolute center, and that's what's driving the whole system. And now if you follow the bottom plot graph, you can see that it's just finishing up its path, and then it's just going to reset and go back around the other way. And that finishes up our simulation.